now is the time to get on like Spike Lee said, get on the bus. Go get your work and keep your people chirping.
Welcome to the video on calculus of vector-valued functions. So in this video, I'm kind of just going to go over, because in the previous video, we went over vector-valued functions and what they are. And it's basically having curves or functions, and each point is defined by a vector that is based at the origin. So the calculus of vector-valued functions is going to be much like the calculus of normal valued functions, of normal like just point functions, right? Coordinate valued, like x and y, and z for that matter. Okay, so first of all, we're going to start off with limits of vector-valued functions. Okay, I'm going to abbreviate it like this. VVF stands for vector-valued functions. Okay, so you don't have to like watch me write out the entire 3 words there. Okay, so we have our r of t, which is x of t, y of t, and z of t. So this is the parameterized vector notation. So limit as t goes to t naught, so to some other point of r of t, is going to be equal to not a value anymore, not just like a y value or a point, but it's going to be equal to some u, which is a constant vector. Okay, so this u, another way to look at it is component-wise. So what we're going to do, when you take the limit of a vector-valued function, so of r of t, you're basically taking the limit of the left side, so that means you're taking the limits of the right side as well. So what we're going to have is actually, component-wise, this is going to look like this, okay? So the limit as t goes to t naught of x of t, same thing here, limit as t goes to t naught of y of t, and then over here, we're going to have limit as t goes to t naught of z of t. Sorry that didn't fit in there, but I just kind of wanted to continue the flow there. Okay, so this is what it is component-wise, and these individually are numbers, right? So limit of x of t is a number, limit of y of t is a number, and limit of z of t is a number. Okay, and additionally, a vector-valued function is continuous if, and remember when we weren't dealing with vector value, but just normal functions, a function is continuous if the limit that it approaches, if the limit as t, or as some value approaches another value of that thing, of that function, equals the value of the function at the point that the variable is approaching, okay? So this is the definition for continuity of a vector-valued function right there in that little box in the left-hand corner. Okay, so now on to, we covered limits just briefly. Again, like I said, a lot of this stuff is going to work the same way as you know before. A lot of calculus that you already previously learned. Now we're just adding like vector notation to things. Okay, so the next thing is differentiability. Differentiability. There we go. Okay, that's quite a lengthy word. Okay, so differentiability, r of t, so r arrow of t, our vector-valued function, is differentiable if the following. So if limit, differentiable, okay, I should add at t, so if, okay, that goes there. And then if the limit as h goes to 0 of r of t plus h minus r of t over h exists. Okay, so this is the definition of differentiability if this limit exists. And then also, so additionally, or also, r prime of t, so the first derivative of this vector-valued function, equals d dt of r of t, right? So the first derivative with respect to t of our vector-valued function, which is equal to the limit as h approaches 0. Sorry, that's a 0 there. That is a really weird 0. As h approaches 0, there we go, of r of t plus h minus r of t over h, okay? And also another way to write this is r prime of t. Another way to think of it, if you're given the components of r of t, then r prime of t is just going to be the first derivative of each of the component functions, or each of the parametric equations, okay? so z prime of t. All right, and so basically what this is saying is that r of t, our original vector valued function, is differentiable. I'm just going to abbreviate, differentiable if and only if its component functions or components are. So by components, I just mean the x of t, the y of t, and the z of t. And all three of those have to be differentiable in order for r of t to even be differentiable. Okay? You can't have two that are differentiable, the x and the y, let's say, and then the z, for some reason, is not differentiable. Then that means that our r of t is not differentiable overall. Okay? All right, so now let's do an example. We're going to do the following. Calculate. We're going to do some practice here. So r double prime of 2, where r of t is equal to the following. T to the third, comma 7t, comma e to the t. Okay? So to get there, we just have to calculate both of the first and second derivatives. So for r prime of t, we're going to differentiate the first component, so 3t squared, that's for the x. That's x prime of t. Y prime of t is just going to be 7, and z prime of t is just e to the t. Okay? All right, so now we actually need to get to the second derivative, so we're going to do this once more. So we're going to have a 6t here, a 0, and an e to the t. Okay? All right, so now we're almost there. We just need to plug in a 2 into this second derivative. So if you plug in a 2 for t, what we get is 6 times 2, 0, and then e to the 2 power. So this is going to end up being a 12, 0, and e squared. Okay? So that does it for that problem. Pretty simple, right? Okay, so now let's go on to rules for differentiation.
Let your paper stack instead of going overkill. Pay your fucking people bill, bitch.